Hey folks, in the previous video we talked about the thought process behind linear regression, what is linear regression and where we use it. Now in this video we're going to talk about the algorithm. We always get started with the data. Now let us say we have collected some data on housing prices. We take an example of housing prices. So since we are talking about univariate linear regression, we will talk about only one factor that's involved in predicting the housing price. Now we have the x column and the y column, the x being the size of the house in square feet and the price. So given a size of the house, we will predict the price of the house. So that's what our aim is. We always collect a lot of samples. These are all the data points that we have now. And each data point is a training example. Now let us say we have M training examples like this. And each of this data point in the X column is an input variable for our hypothesis. And this would be the output. Now X is also called as a feature variable. Now we have one feature and Y will be the target variable. Now as discussed in the previous video, when we plot the data points into a graph, then we see a trend in that data. Now we need to fit a model into this data, some sort of a linear model. Now for any given input, once we fit the model into the data for any given input, let us say, we can easily predict the price of the house. So to do that, we need to build some hypothesis that could take in the size of the house as an input and give an estimated price. So that's the output. Estimated price will be the output. Now that we have the training set is nothing but the data samples that we collected. Now we need to build a learning algorithm that can tweak the hypothesis so that we can get more accurate price. Now, based on the data, we need to build a proper hypothesis that can take in the size of the house and then estimate the price of the house. If we need a proper estimation, then our hypothesis should be proper. So, to build a proper hypothesis, we need to develop a learning algorithm. So, how can we tweak this hypothesis in such a way that it can give pretty accurate output? So, we have the data. So, using the data, we'll feed it to the training algorithm. And this algorithm will take this data and then tweak the parameters in the hypothesis function that can take in the size of the house as an input and make a pretty good estimation of the price. Now the question is, how do we represent this hypothesis? We represent the hypothesis using this equation. Let us say the hypothesis is parameterized by theta. So it takes in the input x. This will be the size of the house. And then we have parameters, two parameters. One is the bias terms, that is theta 0, and then theta 1, which is multiplied by x. This is a linear equation that I'm talking about. This is nothing but y is mx plus c. I'll put c here, plus mx. This is equivalent to equation of a straight line. If our hypothesis is good enough, it fits the data very well. So that totally depends on the two parameters, theta 1 and theta 2. I mean, theta 0 and theta 1, let us say. Now, if these two parameters are not optimized, then the line could be anywhere else, somewhere else, like this. This is not a good hypothesis for us. This is a good hypothesis. Now, how do we tweak this theta 0 and theta 1? This is done by our algorithm, which takes in the data and then computes theta 0 and theta 1 over number of iterations. And then once it finds out that um, the parameters are optimized, then it will stop learning. And then the final theta 0 and theta 1 that we end up with uh, are the optimized parameters. Now, consider this hypothesis equation where h of x equals theta 0 plus theta 1 multiplied by x. Now, this x is our, size of the house. For any value of x, for any size of the house, we will compute these two terms and find out h of x. Now, what is this? This is the predicted price of the house. Now, let us consider a data point here, somewhere around here. This is one of the samples that we have collected. If our hypothesis is good enough, for a given price around, for a given size around this range, let us say, we can make a good prediction which is closer to this value. What is the price of this particular house, whatever it is here? Let us call it price A. It will be very much closer to the predicted value, very close. Now the training data is scattered on this XY plane, right? We are trying to make a straight line here. Now that passes through the data points. The idea is to get the best possible line here. So that can happen when we choose the right parameters, theta 0 and theta 1, so that the predicted value h of x will be very closer to the actual value. This is where we will try to bring a function where we can measure the accuracy of this hypothesis. That is where cost function comes into picture. Let's talk about cost function. To give an idea, when you randomly select the parameters theta 0 and theta 1, the line might be somewhere. It can be here, or it can be here, or it can be here, or it might be like this. It depends. So over a number of iterations, you are going to change or tweak these parameters to fit the data. So that is the overall idea. Now, to measure how accurate the prediction is, or to find out how well the hypothesis function is doing, there has to be some mechanism. So, what exactly is a cost function? It's a it's a way to measure the accuracy of our hypothesis function here. First thing what we want to do is take a difference between the predicted value and the actual value, right? So this would be our predicted value, h of x, parameterized by theta, of course, and the actual price of the house, that is y. This is for one data point. We had collected number of data points. So for one of the data point here, we have computed the cost. Now we want to take a mean square of this cost. So squared. Now we want to compute the cost over all the data points. So we would write this equation in this way. We want to summate over all the data points. Now we have m training examples, that is the number of samples that we have taken. Now in mathematical terms, we will start from first training example until m, and then we want to compute this for each example. So we will write a superscript I and y of I. You might have seen this equation. So I is one training example. It starts with 1 and then goes up to m training examples. And I want to take an average of this. So 1 over m. So the if you compute the cost over the number of training examples, you will get a number that is j. Let us call this function as j. Now this is parameterized by theta, theta 0 and theta 1. The cost depends on these two terms, theta 0 and theta 1. Now if these two terms are well optimized, our predicted price will be accurate. If our predicted price is accurate, the gap between the predicted price and the actual price y will be very less. So if the difference is less, our cost becomes less. Once the cost decreases, once we minimize the cost to as much low as possible, it means to say we have optimized our values theta 0 and theta 1, and then we can conclude that our prediction is better, it is more accurate. What exactly are we doing here? For each training example, we will compute the difference and then we'll summate all the differences and then we'll take an average. That's exactly what we are doing. And then this function totally depends on theta 0 and theta 1. And that's why we call that function as j parameterized by theta 0 and theta 1. So our main aim is to minimize this cost function j of theta 0 and theta 1 so that we can get the best possible hypothesis. For simplicity, let us say we have 3 data points that we have collected. So for a house of size x1, it costs y1 dollars. Similarly, for a house which is of size x2 costs y2 dollars. So if our hypothesis is good enough, then it has to pass through all these data points. If our hypothesis is not good enough, uh, then it might be somewhere else, like this. Initially, we would choose theta 0 and theta 1 randomly, and then we would keep optimizing it by calculating the cost. We first calculate the cost, and then we'll see if the cost is very high. We will tweak these two parameters. Again, try computing the cost, see if it has decreased or increased, and then again tweak these parameters accordingly. So once you start with a random theta 0 and theta 1, the straight line would be somewhere else. And the gap between the data points is very huge. So the cost will be very high because the predicted value here will be much different when compared to the predicted value um, by the optimized hypothesis function. So there's a lot of gap between uh, the best hypothesis function and the worst one because there is a lot of gap between the predicted values. Once we have optimized these two parameters, the cost function, the difference between the predicted value and the actual value becomes zero. So once the cost becomes zero, it means to say that our algorithm has learned. Or in other words, we will tell that we have trained the model. If we try to plot a graph against theta 1 and the cost function, let us say j and theta 1. Let's forget about theta 0, the bias term. Now initially the cost will be very high And as you keep tweaking the parameters to get the predicted value closer to the actual value, it decreases over time, over a number of iterations. In each iteration, you would tweak these parameters. So this is where gradient descent comes into picture. Let's talk about gradient descent. So over a number of iterations, we would have reduced the cost by tweaking the values of theta 0 and theta 1. So it would saturate at some point in time. This is where you would conclude saying it has reached a global minimum. This would be the value of the cost over a number of iterations. So when the cost function is at the bottom, that is, its value is at the minimum, means that we have succeeded in fitting the model. When the cost is at the global minimum, it means that the prediction would be much closer to the actual value. So the difference between the predicted value and the actual value will be very less. Our aim is to make this function j of theta 1 and theta 0 as low as possible. So to make this happen, we need to adjust these two values. First, we will start with arbitrary values, theta 0 and theta 1, random values, and then we would start tweaking it. For us to tweak theta 0 and theta 1, we want to subtract something. So theta 0, theta 1. In each of the iteration, we want to change these values. So let's try subtracting or adding some term. We'll have a minus here. We always subtract something. And then this term here, whatever term that we have, can be a negative value or a positive value. It should depend whether I want to subtract or add. We can have a positive sign here also. That's totally up to you. It can be plus or minus, anything. But in general, we would always subtract. And this particular term totally depends on the cost function. Based on the cost, we will subtract something from the actual parameter and then update it to a new value. So over the number of iterations, as we approach closer and closer to the global minimum, we want to take smaller steps because we don't want to tweak the parameters too much so that the cost would decrease. So this term here can definitely not be a constant. This would vary on the cost. And also, we can't directly subtract the cost from this term. There has to be some sort of a proportion that we have to take. And also, if the step size has to vary, if we want to change the amount by which we nudge these two parameters, then we have to find out a way how we can do that. Since we are considering only one feature, that is x, the size of the house alone, only one parameter is involved, keeping the bias term aside, that is theta 0. When we compute the cost for each of the theta value, um, in the beginning for a random theta value, it can be very huge, and over the number of iterations, you might have reached a global minimum where the cost has been significantly reduced. So when the cost has been significantly reduced, whatever theta value here will be the optimized theta value. If you use this value in our hypothesis, then our prediction will be accurate. Now let's draw a tangent to this particular curve. By drawing a tangent here, we can find out how steep the slope is, right? We have we have a change in theta here, and then we have a change in the cost. How much change in theta causes how much change in the cost? So that would be delta j divided by delta theta. This is the change in theta, and this is the change in the cost. Now there is another way to do it. There is another way to represent the same thing. Since our focus is on the cost, we would write this as partial differentiation of cost with respect to theta. Now we would call this as a slope. The slope of the tangent is the derivative of the cost at that point. So that will give us the direction to move, where exactly we need to move. This derivative or the slope will be positive or negative based on where exactly our cost is located. The slope of the tangent here at this point will give us the direction to move towards. Eventually, in each iteration that we make, one small step towards the global minimum. We make some steps down the cost function in the direction of the steepest descent. So, this is the direction of the steepest descent. So, when I say which direction to move, do we move away from the minimum or towards the minimum? It means to say, are we adding something to the existing theta 1, or do we subtract something from theta 1? That's the main question. So the derivative or the slope that we calculate here will give us what exactly we need to do. Should we subtract a value or should we add a value? So here it would tell us to add some value to existing theta so that we would move towards the global minimum. As you increase theta, the cost decreases. When you cross this boundary, there is a possibility that the cost would increase because for other values, it might not be considered as an optimized value for that particular data. So if the cost increases, then if you take a slope at this particular point, this particular slope would tell us go back. So it would give us a negative value. This is a negative slope. It would send us back. So we would be moving backwards. For a theta value that is less than the optimized value, possibly it would give us a positive derivative that would take us towards the optimal value. So when I say we are trying to optimize the parameter, we want to subtract something from the existing value, and so that the existing value can be tweaked. This term would be a derivative of the cost function. So when we take a derivative of this cost function, this derivative can be positive or negative based on the randomly initialized theta 1. If randomly initialized theta 1 is somewhere around here, somewhere around this range, then the derivative would be positive, so that theta 1 will get reduced over the number of iterations. If randomly initialized theta value at the beginning of iterations is somewhere around this range, then the derivative would be negative. So that negative into negative, it would become positive, and then over the number of iterations, we would be adding some value to theta 1 so that it would take us over positive values, and then over the number of iterations, we would reach the optimized value where the cost is less. So, how exactly does this subtraction work? If the slope is very steep, it means to say that the derivative is a larger value. So, when the derivative is a larger value, you would be subtracting a larger value from the parameter. So, when you subtract a larger value, it means that when you have initialized theta somewhere around here, the cost function will be very high at the very beginning. Once you have calculated the derivative, you would be subtracting a larger number. So the difference between first value and the next value will be bigger. And the next point will be this. And the cost would have reduced significantly compared to the previous one. So as you compute the cost and reduce the theta over number of iterations, you need to take smaller steps. As the slope decreases, so if you say this is the slope, the amount of change in x compared to the amount of change in the cost compared to the theta will be lesser compared to the change when the slope was greater, that is at this point. In the consecutive steps, when we try to reduce or nudge this parameter, we need to take closer steps. We shouldn't be nudging this too much so that we cross this optimized value. As you get closer and closer to the optimized value, take smaller steps so that we wouldn't miss this particular value. If we take larger steps, let us say this was the value in um, say 10th iteration, and then this would be the 11th one, and this would be the 12th one. We already missed it. So if the step size is bigger and bigger, then the cost would again shoot up. So we don't want that to happen. That is an undesirable situation. So what we would do is we would multiply some value to this derivative. Let us say alpha. So this alpha is the step size. This term alpha is also called as learning rate, how fast we would learn. Over the number of iterations based on the step size, it would take smaller steps or larger steps. That is a term that we would calibrate. We want to use the gradient of the cost function to descend to the lowest point in that cost function. And this is the reason why this algorithm is called as gradient descent. So finally, we would write our algorithm this way. For a parameter theta, we want to optimize this parameter. So in each iteration, we want to update this parameter. So from the existing value, we want to subtract some term. And what is that term? And that term is a derivative of the cost function j with respect to theta. And a term was multiplied, and that's the learning rate or the step size. Remember that we had two parameters, that is theta 0 and theta 1. So both of these have to be optimized. We would write the same thing. And alpha multiplied by the cost. And this symbol is a partial derivative. Now the question is, how do we compute this term and this term? However, these two are constants. Now let's start with the cost function. As we know that we are taking the differences between the predicted and actual values, we are adding those up, and then we take an average. Now if we want to find out the derivative of this cost function with respect to theta 1, in the sense we are treating this theta 0 as a constant and this as a variable. Now apply the same thing on the right hand side also. If we do that, we take 1 over m common, we take it outside. As this is a constant, we would not do anything to this term. Now the summation would be as it is over the number of training examples, and then we would take this value, we would multiply it, whatever the power to which this term is raised to, we would multiply that. and then we will have h of theta of x minus y multiplied by x. The reason being, we had h of theta of x, that is theta 0 plus theta 1 of x, correct? Now, when we are taking a derivative, we are treating theta 0 as constants. So this will become 0. Derivative of this term becomes 0. And the remaining one will be dou by dou theta 1 of theta 1 multiplied by x, correct? Now this term becomes 1. 1 multiplied by x is x. So that's how we end up with x term here. I will try to expand this function so that you can understand it better. So here we would multiply this function with the term again, dou by dou theta 1 of h theta of x. Now the value of this term is x. So our final equation will be 2 over m multiplied by summation of predicted value and the actual value multiplied with x. Usually this mean that you see here is halved for the convenience for computation of gradient descent. So when it is halved, this 2 will be cancelled. We will end up with 1 over m multiplied by the remaining terms. However, this is for the derivative of the cost function with respect to theta 1. When it comes to theta 0, again this will vary. So when it comes to theta 0, we would differentiate this term with respect to theta 0, and then we would, as a chain rule, we would differentiate this particular term with respect to theta 0. When we do that, the differentiation of the hypothesis with respect to theta 0 will be theta 0 into plus theta 1 into x. Now differentiation of theta 0 with respect to theta 0 will be 1, plus we want to differentiate this term theta 1 of x with respect to theta 0. Now this will become 0 because since we are differentiating this term, hypothesis term, with respect to theta 0, we would consider theta 0 as the variable and theta 1 of x as the constant. So constants, when you differentiate a constant, it becomes 0 and this would be 1. So this term here would not be x, instead it would be 1. Now let us not forget, our main aim was to optimize theta 0 and theta 1. Now to optimize theta 0, we would subtract some value from theta 0, and that value was alpha times derivative of cost function. And similarly for theta 1, it would be the same. Step size multiplied by the derivative of cost function with respect to theta 1. Now this term here would be 1 over m multiplied by the summation of hypothesis function subtracted by the actual value. And this term would be 1 over m multiplied by the summation of difference between cost function and the actual value multiplied by the feature itself, that is size of the house. And this is for each training example, that is for each sample data that we had. So let's have a superscript I that will represent for which training example we are computing this cost, and x of I. So to summarize, m will be the size of the training set, the number of sample data that we have, and alpha will be our learning rate or step size. I here will denote which training example are we pointing to, or the index. And theta 1 and theta 0 are the parameters or the coefficients of the feature x, meaning the size of the house. And finally, y is something that is the output, that is the actual outcome of ith training input. For so and so size of the house, y was the price of that house. And h of x is the hypothesis. This is parameterized by theta 1 and theta 0, which is a function of x. It takes in the size of the house and then predicts the price of the house. We want to compute theta 0 and theta 1, these two parameters, and we want to nudge these two by subtracting some value in each iteration. So we want to do this computation over and over again until we reach the global minimum in the cost function. Once it has reached the global minimum, it means that we have optimized these two parameters, and we can conclude saying we have trained the model and the model has learned the data and it is able to predict the values accurately. Now let's try and implement this algorithm in Python. In the next video, I'm going to show you how to develop code for this algorithm using Python and NumPy library. We are going to build this algorithm from scratch without any other machine learning framework. So you can code along with me and learn how to develop code for this.